Did we do our head count of the bus? Make sure everybody's on board.
Yeah, no one's still in the bathroom here.
Yeah, no one's still in the bathroom. And do everyone have their booklet? And we're ready to roll.
Don't want to leave anybody behind.
Don't want to leave anyone behind. Absolutely. And so if so, then I'll introduce our first presentation for today if we're ready to roll. All right. So we have speaking from Fairfield-Suisun Sewer District, Jordan Demerol, who's the chief engineer, and also Ben Carver, who's the operations supervisor. And so they'll be telling us that, well, they'll tell you what they're going to tell us about. And so I'll turn it over to them now, Jordan and Ben.
Thanks, Robert. And thanks everyone for joining us today. It's a interesting way to do the bus tour this time, but it's a lot shorter drive up to Fairfield when you can just stay where you are. So today, Ben and I are going to talk about the blower replacement project that the district just completed about a year ago. This was a project to replace a number of assets at our treatment plant. And we decided to use a newer technology for our blowers. Not cutting edge, you may have seen them around before, but we thought it was a good learning experience. And so we wanted to talk to you a little bit today about the project, about some of the lessons we learned, and about looking at the project from both the engineering side as well as from the operations side, how it's benefited us and simplified our biological wastewater treatment process. So let me start with a little bit of background about the sewer district. We're a special district, not affiliated with a city or a county. We were established in 1951, and we provide wastewater conveyance and treatment within the cities of Fairfield, Suisun City, for Travis Air Force Base, as well as for portions of unincorporated Solano County. We also provide operations and maintenance management of the stormwater drainage system throughout the cities. These are some of the key stats of our agency, the big numbers that everyone likes to look at to get a sense of magnitude. So our treatment plant is rated for 23.7 million gallons per day. We currently operate at an average dry weather flow of about 11. So we're only using about half of our capacity so far, lots of room to grow. The district owns 85 miles of gravity sewer, 12-inch and larger trunk sewers, as well as a number of force mains throughout our service area. And we serve approximately 140,000 people throughout the area. So I'm gonna highlight some of the elements of our blower replacement project. And there's a lot of text on this screen, so I'll go through it relatively quickly and then we'll look at some photos. We had a few main goals with this project. It was primarily a renewal and replacement project, replacing aging assets that were operating inefficiently and operating not as reliably as we would prefer for a essential service like wastewater treatment. So we had a 20-year-old Turblex blower, a 600 horsepower blower that provided aeration air to our secondary treatment process. That had operated basically 24/7 for 20 years. So it had a lot of run hours on it, and we didn't have a great backup system. Our backup system was a number of 40-year-old, really large 1,250 horsepower electric blowers, and we had a diesel engine-driven backup blower. So we didn't have backup power to our blowers, but we had to start a big diesel engine when the power went out. So again, old assets, not extremely reliable. We also wanted to look at our aeration capacity today and into the future. We were beginning to reach the maximum of what our blower could produce. And we know that there is a fair amount of growth planned for especially the northeast part of Fairfield up towards Vacaville. There's a lot of new development in that area, and we wanted to make sure we have capacity to serve them. So we did an analysis to right size that capacity. And we also wanted to look at our control system. There are newer ways to control a blower system that aren't just pump the pipe up to a certain pressure and and hope that everything works right. So we implemented a most open valve aeration control system that we'll talk through a little bit later. From an electrical standpoint, our prior blower system all operated on medium voltage, 4160 volts, which for those of you that aren't familiar with the technical details there, I'll just say that's a higher voltage than we typically like our staff to work on. You have to have special training and safety devices. So that meant that anytime we needed to work on this system, we were hiring a contractor to do so. We wanted to address that and bring everything down to a lower voltage, 480 volt, so that our staff could operate and maintain the equipment. The electrical equipment in general was just as old as the rest of the system, so we replaced much of that. And then in terms of backup power, the blower building also housed a large 800 kilowatt diesel generator that provided backup power to about half of our plant. So that was also original to the plant, and we needed to replace it for reliability purposes. And we also increased the size so that it could now provide electrical backup power to our new blower system. So here's some photos of the equipment we took out. You'll notice some, really bright old 70s colors and, lots of corrosion and oil stains from years and years of successful use. So this was one of our large 40-year-old electric-driven blowers. And over here on the right side was our diesel engine-driven blower. So a huge piece of equipment, made a ton of noise, lots of exhaust, pretty nasty when it was running. This was our big diesel generator here in the lower left corner. And then this was, on the lower right, was the original motor control center lineup, which, looks okay from the outside, but the internals were old and wearing out. So we put together a project. The total project cost ended up coming to about $10.5 million. The project was designed by Carollo Engineers. Our contractor was Overa, and our system integrator or programmer was Telstar Instruments. And we essentially addressed all those elements we just talked about. 4 new high-speed turbo blowers to replace our old aging blowers, a new 2 megawatt standby diesel engine generator, new electrical equipment. We installed a new aeration header pipe to distribute that air to all the places it needed to go, and a new control system that included this most open valve component, and better integrated our blower controls with the aeration system controls in general. So from an engineering point of view, I wanted to talk through a few of the elements that we thought through and thought about as we were designing the project. The first is the blower technology itself. There are a number of different technologies available for aeration blower systems. We really narrowed it down to 2 types: a single stage centrifugal blower, which is essentially the technology we used previously, as well as this newer technology, high-speed turbo blowers. They've been around at this point for a little over a decade. So like I said, not necessarily bleeding edge of technology, but still on the newer end of the technology we use in our industry. What we found as we really analyzed the products that were available on the market is that these different technologies have different sweet spots in terms of the efficiency of producing air for the amount of power you put into it. And depending on where your air demand lies, it's really going to influence what technology is the most effective for you. So the way we captured this for our particular design point is we prepared an equipment pre-selection bid before we finished designing the project. And we essentially competed centrifugal blower manufacturers against high-speed turbo blower manufacturers. And rather than a typical bid where we ask for a capital cost, a price to install the equipment, we actually put together a form that prepared a life cycle evaluation. So we had them insert their maintenance costs. We had them guarantee the power draw that we would use over the lifespan of those blowers, so that we could really compare the efficiency aspects of the blowers as well as the upfront price. So we wanted to capture the fact that, you know, maybe one technology would cost us $500,000 less to install, but if it costs us $10 million extra in power over the lifespan of the project, then that's really not our best option. And so this was a way that we were able to select the high-speed turbo blowers based on the design point, the amount of air that we needed to produce and the pressure we needed to produce it at. The high-speed turbo blowers came out pretty significantly lower on a life cycle basis. And so it just made more sense. Now, if our air demand were twice as high, that may have turned out differently, but just based on our specifics, that's what made sense for us. The other thing that we wanted to account for was the O&M costs, and really beyond the costs, the frustrations and challenges of maintaining the equipment. And so in order to make sure that we weren't missing something and being misled by manufacturers about how maintenance-free their equipment was, we surveyed a number of agencies, and I probably spoke with some of you on this meeting, to evaluate, you know, what different agencies' experiences had been with these technologies, what problems they had seen. And we were able to do that during design phase so that we could mitigate those during the design, make sure we you know, avoided the pitfalls that others had seen before. And that was a really helpful step to get everyone on board and make sure that we were all comfortable with the direction the project was going. And then the other thing, which maybe seems kind of obvious, but I think as engineers, sometimes we get excited about the future and where the world is going, but we need to make sure to take a step back and make sure that it works today as well. So some of the problems that we had heard about from other agencies were that, you know, the blowers were perfectly sized for some future point, but not very well suited for today's air demands. And so, you know, I just wanted to highlight that's a good thing to pay attention to as you're going through a design. Make sure that you consider today and tomorrow so that you don't run into problems. So here's some of the new equipment we installed. In the upper left here are 2 of our 4 new high-speed turbo blowers. You can see that basically we fit 2 blowers in the footprint of one of those large original blowers. So it really saved us a lot of space. They're much quieter, they're much simpler to operate, and Ben will touch on some of that in a little bit. On the upper right here is our new engine generator. So again, it's actually a slightly smaller footprint despite the fact that it's over twice as much electrical capacity. Just speaks to the improvement of technology over the last 40 years. Our new electrical switchboard and distribution system, much more modern, more feedback to our plant SCADA system so we can monitor what's happening. And then here in the lower right is the new aeration header that we installed. We ended up going with an above ground air header, which you know, some of us wanted to paint a bright fancy color, but we ended up with boring wastewater treatment plant gray. But this really helped with sequencing of the project so that we didn't have to disrupt the buried existing line while we installed the new line, and we could have a one-day switchover. Made it really simple. And then this is a before and after photo of our blower building. So here on the upper photo is the before. You can see a lot of older equipment, these large orange diesel engines, and you know, just generally more clutter. And then in the lower photo here is the new engine generator, new electrical distribution equipment, and our 4 new blowers and air piping. Really clean, really nice, a lot smaller footprint, and about twice as much air capacity for this system as we had in this original system. And the last thing I wanted to touch on before I pass it over to Ben was our funding. We did finance this project through the state revolving fund. And I recognize for those of you who have looked into state revolving fund, it is the situation is much different today than it was 3 years ago when we secured this funding. It's a lot tighter and a lot more impacted, but this is essentially the state provides low interest loans to allow you to cheaply finance the installation of essential water and wastewater equipment. But the beautiful part of this whole story is that because of the significant increases in efficiency that we were anticipating from the existing equipment to the new equipment, we applied for and were awarded the SRF's Green Project Reserve status, which essentially grants you a principal forgiveness on your loan. So we were awarded the full amount of $4 million principal forgiveness. So that's basically 40% of our total project cost was forgiven by the state. So we essentially paid $6 million out of pocket for a $10 million project, which was a huge win. And the analysis really was not too difficult. You compare nameplate efficiencies between the old system and the new system, and you show that, you know, from higher efficiency equipment, from modifications that we made to our treatment process based on those equipment changes, and our improved control strategy, we were easily able to attain a 20% energy savings for our aeration system. So, you know, really worked out well for us. I did want to note that a lot of people avoid SRF if they can because it's time consuming and it's working through the state. And it certainly was, and I won't sugarcoat that. It delayed our project probably by a year. And there were some frustrations along the way of, you know, checking all the boxes for federal funding. But it was worth it in the end because we saved 40% of our project cost. We also got $50,000 back from PG&E for energy savings. So all of you in the PG&E service area, make sure anytime you make a treatment plan improvement, you talk to PG&E. They're usually very willing to work with you and give rebates for energy savings. So with that, I will turn the floor over to Ben Carver to talk about some of the O&M considerations.
We just want to point out some of the biggest O&M considerations, things that we had anticipated, but also things that kind of came to light during this project. So of course, one of the biggest things is power cost. Significant energy savings by just switching to a different type of technology. What was also interesting is our plant is unique where we have two different biological systems. We have an activated sludge system, but we also have these what we call oxidation towers. They're basically large roughing filters. So because of our old system, our Turblex blower was reaching its capacity. So because of that, we had to run our two different biological systems together. And what that did is it created a deficit in carbon to maintain our activated sludge system. So we were playing this game between, you know, not having enough carbon or not having enough air, right? And we couldn't switch to our 40-year-old blowers because then it was way too much air because they were designed with a different aeration system. So by switching to these blowers, not only are we saving power, but we're actually also able to shut down one of our biological systems. So there was also significant power savings there. Now, of course, that means we're using a little bit more air than we used to use. So that might look like we're using a little bit more energy. But as Jordan brought out, we did a full analysis, and actually we still come out ahead as using less energy when you look at the plant as a whole. As an additional benefit to that, now our activated sludge process it works so much easier. It's just such a better system now. So as Jordan brought out, we did go with the high-speed turbo blowers. Biggest benefits there is it's a very simple piece of equipment. It reduces the many number of parts as compared to our other systems. With our Turblex and the others, we were having a very hard time finding the appropriate parts because, again, these were aging equipment and maintenance was becoming very, very difficult. But the Neuros turbo blowers are very simple, really, and it's easy to do work on them. The one thing about the turbo blowers is they are very sensitive to dust and dirt particles. So you have to keep that in mind. You want to keep the area very clean, and you want to change out your filters regularly. And I'll talk about that here in a minute. We have a quick video to show you what that looks like, just to show it's actually a really simple process. So there's a little bit of labor there, but it's still much better than the system we had. Jordan mentioned the aeration control system. So it was a little bit of a challenge during when we were bringing these turbo blowers online. The way we had to sequence it, we had to bring part of our activated sludge process up on the new system while still maintaining the old system. And then we had to tune that new system and then switch them and then tune the old system. So it was a little tricky. I think our recommendation would be, if you go with a new blower system, have the manufacturer send their programmer either on site, or if they can remote in, and put that in the budget so that you can pay integrators to work on the system. It took us about 2 weeks just to sit there and fine tune the control loop there. It was a lot of work at first. It was a steep learning curve for the operators themselves learning this new system, but you put in that work, you get through those 2 weeks, and it's well worth it. So it works very well now. Electrical system, as Jordan brought out, the old system was very hard to maintain and to work on. Now that it's all 480, we have qualified staff that can address all those concerns. And what is also a nice feature is no longer having a diesel blower that we have to rely on. Now, whenever we experience power outages, especially during PG&E's PSPS events, we have a large enough generator that can run all of our blowers. So just reliability during emergencies has greatly been improved on, and we're just very happy with the system we have now. Let's go ahead and, so this is a quick video of what it looks like to change out the filters. Like I said, it's a very easy, simple process. All in all, it really only takes about 20 minutes. We have our operator first conduct a lockout tagout process, which he's already done. It's not in the video. But here he's just dusting off the louvers, and he's going to replace what we call the pre-filter. We do that once a week for every blower. And then during these times where it's been heavy smoke, we've had to do it a little bit more often with the pre-filters. But even then, it's only a 15-minute job per blower. So that's the pre-filter is taken off. And now he's removing what's called the main filter. And that's what's really protecting the core. The main filter is replaced about once a month, maybe every 5 weeks. It runs off of how many hours the blower runs. He's adding some Velcro, and then he puts on the new pre-filter, and that's it. That job probably takes about 15 minutes. It's really simple. And then on the front of the blower, you have the VFD cabinet, which has its own little main filter and pre-filter that needs to be changed out as well. But all in all, it's just a real easy, simple process. And then in our next video, we'll kind of show you the inside of the blower, the core itself. So we open these up about on a quarterly basis. Our mechanics open it up, they take a look, and as you can see, it's real clean in there. So it's been about 3 months since we've cleaned inside that core, but it's still super clean. Here we have our cooling pump, oil reservoir. As I mentioned, it's a really simple piece of equipment. And there's the blower core itself. So footprint-wise, it's very small compared to our massive Turbolex blowers and 40-year-old blowers we used to have. Yeah, and so that's done about quarterly. And then beyond that, we have a annual maintenance that we do, and either we'll do it or we'll actually have Neuro's technician come out and do that. So as far as the maintenance side of things, it's very low labor hours is required. Very little maintenance. They run great. The program works great. And that's really it. So I think at this point, we could probably answer any questions.
All right. Great presentation, Jordan and Ben. We do have some questions in the chat, and we'll address also if there are any raised hands. But there's about 3 or 4 questions here in the chat that I'll ask you guys, and we'll start there. So here we go. Did you consider APGs, dual core blowers, to save even more space?
Yes, we did consider that. Neuros makes a dual core blower, which is essentially two of those, the core that Ben showed you in the upper section. It's 2 of those in the same package. So it simplifies the installation. You have one blower box with basically double the air capacity in it. We did look at those. We had some concern about the reliability of having, you know, a single VFD and a single cooling system. Potentially, if you have an issue with one of those common components, you now take out half of your air capacity rather than 25%. So we did consider it. We opted to stick with the single core just to increase the reliability.
Okay. Another question is, your air header to your basins look to be DIP. Did you consider SS at all? I visited lots of treatment plants and all of them seem to utilize SS air headers. Just wanted to know your thoughts during design on this.
Yeah, we certainly were, we did explore that. The price difference is pretty significant, and ultimately that was really a value engineering decision to make sure we stayed within our project budget. So it's a carbon steel pipe, welded carbon steel, coated on the outside and uncoated on the inside. What we found in the past with our air headers was that the interior develops a little bit of a sort of a rust lining, which sounds bad, but because there's not a lot of abrasion and not a lot of water in there all the time, that provides a pretty good internal coating. We also found that it was more economical to make the pipe a little bit thicker than we would have if we had gone stainless. Than going stainless. The cost difference was actually cheaper to get thicker carbon steel pipe rather than stainless. So we increased the thickness by, I think, about 1/8 of an inch, just to give us a little bit more sacrificial thickness and come out ahead economically.
Okay, great. Here's another question. With the programming, were there any issues in programming cycling of the blowers related to lead and lag, etc.? Also, do you have a flex cycle requirement for your diffusers, which requires the blowers to shut off completely to let the diffusers settle back to their original state before turning back on?
Ben, do you maybe want to talk about the controls?
Yeah, we didn't have any issues programming the lead lag. We kept that part of the programming very simple. It's just a simple numerical, it goes in numerical order, 1, 2, 3, 4, and then the operators have the options to change that lead lag position as they wish. So we just kept that part really simple, and we really didn't have any issues in that regards. The only issues we came across was programming how the response time of our air valves, how much do they open and how fast they do that, and all that. That was all part of that 2-week integration where our Neuros tech just fine-tuned that programming. So it took only a couple weeks, and then we got it fine-tuned. As far as the flex cycle, we addressed that through a PM system, and the operators manually do that, where they'll actually turn off the air to a particular basin, allow our membranes to collapse, and then they, what we call bump them. Then they increase the airflow to a specific airflow to basically break off anything that might be plugging those membranes up. But we never programmed an automatic cycle to take care of that. We just handle that ourselves.
Okay, great. Any follow-up questions anyone has?
There's
Jimmy?
one more here from Jimmy Dang again. What did you settle on? Oh, did you already get to this? Did I miss that? I'm sorry. What did you settle on for the reaction time for the air valves?
So the way that's set up is the system looks at every aeration basin, and it looks at the DO, and it looks at the difference between our DO set point and what the actual DO is. And then it goes to the next basin, and then the next basin. So about for every 2 minutes, it's looking at the basin, seeing what that delta is, and then it adjusts the valve on a preset percentage. And that's all adjustable by the operators. So really what it comes down to is about every 2 minutes, it's making an adjustment, and it only makes an adjustment about 5% the air valve will move. So it's small adjustments and just a little bit at a time, all the time. I don't know if that answers your question.
It looks like Jimmy Dang's going to be in touch with you guys. I think he's planning on something.
Bring it on, Jimmy.
At Oraloma. What do you think? You've got their information there, Jimmy. So are you guys already in conversation? Or if not, you will be, I believe. Great.
And we have another question, I think, from John Cook. Do you clean the main filters or are they disposable?
So the main filters that we went with, they're a newer type of filter, and you would just replace them. Neuros did have an older main filter that they said you could backwash up to 3 times, but we chose to go with this newer filter and we replaced them.
They're not particularly cheap, but the offset in the amount of labor we spend maintaining these things more than makes up for the price of the filters.